Yeah, company view. Start off. Hope everyone's gone through the notes. Let's see. Last thing we did was this liquids. Great. Next thing is apparent expansion. Just give me a minute. Yeah. Hmm. Great. So apparent expansion. Now, unlike solids, right? Whenever you heat up the liquids, the problem that you face is even the container starts expanding. So when liquids are heated, you just can't heat them, individually. The container also will start expanding. Now, when the container starts expanding, you start getting errors. Example, let's take a scenario here. Let's say we have a container filled with liquid. Let's say it is showing 100. Meaning if you ever seen a beaker, right? It has its own scales on top of the beaker, like your chemistry lab. Now, technically speaking, we know the liquid and the container will expand at the same time, but for convenience, let's assume they're happening one after another. So first let container expand. And when the container expands, the liquid level will drop a bit because the base becomes broader and all. So maybe this will show a reading of 95. Now let the liquid expand. Like I said, in reality, you will see both happening at the same time. Now what you will notice, let's say the reading becomes 110. Now you tell me, what is the actual expansion? If I ask you what is the actual expansion of the liquid, how much is that? If you look at the actual expansion, the liquid actually went from 95 to 110, isn't it? That is 15. But like I said, both happen at the same time, so you'll never actually see the stage. You'll directly go from here to here, isn't it? Then what do you think? You think initially it was 100, finally it is 110. So we call this thing apparent expansion. It is not real expansion. So we have apparent expansion, that is 110 minus 100. I hope you're getting what it means. So apparent expansion is simply the expansion with respect to the container. So after including the expansion of the container, whatever reading you get, that is called apparent expansion. The real expansion is actual expansion of the liquid. So the formula goes like this. The apparent expansion is real expansion minus expansion of container. So this would be V gamma apparent delta T. So the change in volume with respect to container. This is V gamma real delta T. Hope you remember last time we defined gamma is the quotient of volume expansion. This would be gamma. For solids, gamma is 3 alpha delta T. So from here we get gamma apparent is gamma real minus 3 alpha. There, this is the relation between apparent expansion and real expansion. So if gamma real becomes equal to 3 alpha, the containable thing, the liquid never expanded. Means whatever amount the liquid expands, the container also will expand with the same amount. This gives you an illusion, meaning the reading, right? If this is 100, this also will show 100 in the final answer. So gamma apparent or apparent expansion is expansion with respect to container. I'll show you a problem on this. That will be even more, will give more better clarity. There. So whenever you put something in a container and if you expand, this is what you see. You can even get negative also. Let's say container is expanding more than the liquid, right? Then you will observe actually the water level drops or the liquid level drops. There, have a look at this. Clear? Let's see a question based on this. We have a container partially filled. VL is the volume of the liquid. VC is the volume of the container. Gamma L is the coefficient of volume expansion of liquid. Alpha is the coefficient of linear expansion of the container. It's a solid. Remember, alpha is only defined for solids. So the question is, find the condition if the volume of empty space remains constant. It's an easy one. Meaning this volume of empty space which is there. So when you heat up the liquid will expand, container will expand, but I want that red space here to be constant. Then what is the condition? Get this. ये भी यार think it's an easy one. I'll give you another 30, 40 seconds. Find the condition. That means, can I say like this? By whatever amount the container expands and the liquid expands, the difference must remain same. Right, Ishana. Let's see, this was easy. Not sure why you got stuck. So, what is an empty space? So, empty space is V container minus V liquid. So, when you change the temperature, then the empty space would be Vc into 1 plus 3 alpha delta T minus V liquid 1 plus gamma delta T. And you're saying this must remain constant. That means Vc minus equal to VL. So you get Vc3 alpha must be equal to VL gamma. There. If you satisfy this condition, the empty space will remain same. Clear with this? Next one. Next one is a better one. This can be asked as a matrix matching. We have a container filled with liquid. H is the initial height. Alpha container is alpha. Base area is A. Gamma liquid is gamma. Now, when temperature changes by delta T, now you start heating up this liquid or cool it down, doesn't matter. When temperature changes by delta T, you're heating it up, delta T will be positive, you're cooling, delta T will be negative. Then find the height of the liquid as measured from the ground frame. That is the actual height. Second thing, find the height as measured by the scale on the container. So this container, right, also has its own scale. You getting? If you ever seen your chemistry ka lab mein beaker, right? The beaker also has markings, right? Find the height as measured by the scale on the container. Are you getting the difference between both the questions, everyone? I'll give you an example. See, listen, let's say we have a container like this, and this is the liquid. Let's say, example, this was 100 centimeters. Okay. So basically here we have markings like 100 and 50 and 0 and all. Now, let's say when you heat up the liquid, the container ka liquid, let's say it expanded. So it became like this. Now you tell me, in reality, the height of the liquid increased, right? So when I ask you the actual height, the first question is this: find this actual height. That is the first question. The second question, now, when you heat it up, the scale also gets messed up, right? So this will be 0 somewhere, this will be 50 somewhere, maybe this will be 100 somewhere. Meaning in reality, this will still show some reading of 95, isn't it? You're getting the difference? So this, because the scale is also expanding, it will not show the actual value, it will show something else. Is this clear, everyone? So there are two different questions. What is the actual height as seen from the ground frame, and what is the height as seen by the container? So the container is measuring with respect to its own scale, which is also getting expanded, so the reading gets messed up. Is the question clear, everyone? So I'm asking two things. So what is the actual height, right? And maybe if you actually measure, the actual height might be 105, but the container is saying it is 95. Hope everyone is getting the difference there. Try, get them both. It's a good one. So this, I'll show you how they can ask this in a matrix match. But give it a try. Your final answer has to be everything in the numerator, Vihan. That means you have to use binomial approximation. For example, if you get something like 1 plus gamma delta t and 1 plus alpha delta t, you have to bring it up. I taught you last time, remember, binomial approximation. 1 plus alpha delta t minus 1, and then you have to expand 1 plus gamma delta t into 1 minus alpha delta t, and we neglect all the higher powers and we write 1 minus gamma alpha delta t, something of this sort. Because options they won't give like this. They will, final answer will be written in this form. Try. Everyone should give it a try. I'll give you a minute or two. Right, Vihan. That is right. Get the next one also. Anyone confused with the question, please ask. Question is clear, go ahead. Should I show you? Try, I'll give you a minute more. Hmm. So just combine the alphas, Narigod. You and your answer. Who reports an answer like this, right? 1 plus 2 minus 1 plus 3. Just multiply and add them, right? Let's see, everyone. Now, again, the confusion here is the container is expanding, liquid is expanding. So let's do one at a time. So here, initially, how much liquid is there? What is the volume of the liquid? Area into height, isn't it? So I will just take out all the liquid. So the initial volume would be A into H. So that's your initial volume. Now what you did, you expanded this. Temperature changes by delta T and the liquid becomes little more. How much will it become? It will become A into H1 plus gamma delta T. Agreed, everyone? This is the new amount of liquid. Now, in this process, now let's look at the container. So initially your container was like this. The base area is A. Now when you heated this container, temperature changes by delta T. Now see, height of the container will change, agreed, but the base area becomes A into 1 plus 2 alpha delta T. Agreed? Last time we did this thing, areal expansion. Areas will expand by 2 alpha, coefficient of areal expansion. And now what you did, you took this liquid and you poured it inside. Isn't that what happened exactly? When you were heating, then the liquid expanded, container expanded. What I did, I took it out separately, I heated it up. Now when you pour this liquid inside, let the height be h dash, which is the actual height. Therefore, I can simply say the initial volume, which is final volume A into H 1 plus gamma delta T. You took this much liquid, and when you poured in the container, it became A into 1 plus 2 alpha delta T into H dash. There, H dash is equal to H into 1 plus gamma delta T by 1 plus 2 alpha delta T. Now we can use binomial approximation. This will be H into 1 plus gamma delta T, 1 plus 2 alpha delta T whole power minus 1. This is H into 1 plus gamma minus 2 alpha delta T. You can neglect the higher powers. This is your actual height. So in the exam, if they ask you, find the condition, the actual height of the liquid doesn't change. It is gamma is 2 alpha. It's not gamma equal to 3 alpha. Gamma equal to 3 alpha is something else. That is the height as measured by the scale. But have a look at this. Any doubts on this part, please ask me. Then I'll show you the second one. Clear with this? Now what happened? You're measuring this height with a scale on the container. Now tell me one thing. Does the height of this container, does it affect the problem? Why do I care how big is this container, isn't it? The H dash is going to remain same. The actual height of the liquid will get affected only because of the base area. The actual height of the container is useless. And then we studied this thing, in that problem, if you remember, a steel scale is used to measure the wooden stick and the copper rod. This was the reading there. Height as measured by scale is what? The actual height by the factor the scale increases. So the actual height is h dash and the scale is changing by a factor of 1 plus alpha delta t. So this would be h into 1 plus gamma delta t by 1 plus 2 alpha delta t into 1 plus alpha delta t. Again, if I do the binomial approximation, I'll get 1 plus gamma minus 3 alpha delta t. There, here you're getting 3 alpha. This is your reading of the scale. Clear, everyone? So whatever actual height you got, because of the scale you'd messed up, so you'll get one more extra 1 plus alpha delta t in the denominator. So this would be your apparent height. This is the height with respect to container. So container will think this is the height. If you bring your own scale from outside, that will think this is the actual height. I hope you're getting the difference. The difference between these two problems is, in this case, when the container expand, your height got messed up, agreed, but you're actually using a proper scale from outside. In the second case, the height got messed up. On top of it, you're also using a scale which also got messed up. You're getting it? That's a double error. That's you got extra one more 1 plus alpha delta t in the denominator. Is this making sense, everyone? But let's see, let's try to understand what it each means. But any doubts on this page, please ask. Again, I did nothing here. See what I did. I took out the liquid, I heated it, liquid expanded by 1 plus gamma delta t. I took that liquid and poured in a container whose area has expanded and let the new height be h dash. So volume of the liquid that you poured inside must be equal to the volume of the liquid inside the container. Simple, volume conservation. I got h dash. This is the actual height. Means if you bring a proper, a tape which didn't get messed up due to temperature and measure it, this is what you would have seen. Unfortunately, your container also expanded vertically. This resulted in the scale expansion, so your reading get messed up. One of the reason why, if you see in your chemistry lab and all, right, they use borosilicate glass. No one uses metal containers. Borosilicate glass has a very less alpha, even lesser than 10 power minus 5. So the expansion, the volumes, right, the errors won't be large. Even if at all you have to measure volumes, you will make sure you wait till the temperature settles down and then you measure the volume. You don't measure at a higher temperature. Clear with this? Now, normally it's not a big deal, but especially when you're making pharmaceuticals, right? It makes a difference. Let's say the drug cut dosage has to be 2 milligrams, and you got an error of 10%, so you're overdosing the patient with 2.2 milligrams. So yeah. Now let's see what it means actually. Let's say gamma is less than 2 alpha. Now understand, if gamma is less than 2 alpha, this is negative, this is also negative. I think a picture would be more easy to figure out what is happening there. So if this is my container, this was the liquid, the container became big, the liquid became like this. So initially, if the container was showing 100, this will show something like 90. Now, if you actually observe, the actual height decreases. The actual height and reading of the scale both are less than the initial value. Suppose if gamma is exactly to alpha, this is how they'll ask you in matrix matching. So on the left hand side, you'll have like this: gamma is 0.5 alpha, gamma is 1.5 alpha, gamma is 2 alpha. Right hand side options will be liquid height will increase, liquid height will decrease, the reading will decrease, reading will increase, something of that sort they'll play around. So we have the container would expand, this would be the height of the liquid. So if exactly gamma is 2 alpha, if this is 100, you will notice they're exactly same height, but the scale will be showing 95. Getting the difference? So if gamma is 2 alpha, the actual height will be same as the initial height. But because the scale expanded, it will show less than 100. I hope you're getting the meaning now. So actual height remains same. Reading decreases. Let's say gamma is between 3 alpha and 2 alpha. So initially it was 100. The actual height increased, but the reading is still showing 98 or something. So actual height increases, but the reading is still decreases. So basically, this is after temperature rise. I'll write like this. Let this be temperature T plus delta T, and this was T. If gamma is exactly 3 alpha, now this is the meaning of apparent expansion. Container will think there is no expansion. This was 100. The actual height increased. The container will say reading is same. Height increases, the scale ka reading remains same. There. So if gamma becomes equal to 3 alpha, the container will say the liquid never expanded. But we know in reality, in the ground frame, you will observe the liquid level actually goes up. So that's the two questions here. The actual height should not change, then gamma is 2 alpha. Apparent height should not change, then gamma is 3 alpha. So most people will read gamma 3 alpha for this question and come. So that's what you have to be careful about. If gamma is greater than 3 alpha, the initial is at 100, maybe they should show 105. Their height and the reading both will increase. There, these are the 5 cases you can get. Please have a look at this pictures. I think this will give you a better clarity. What do you mean by gamma less than 2 alpha, greater than 3 alpha, and what all those things? Sure, everyone. So if they ask you a question like this, what is the condition that the liquid overflows in the container? When you increase the temperature, what is the condition for the liquid to overflow? Again, so liquid must overflow. Matlab, the container should think the liquid level has gone beyond its own height, isn't it? Container should think. Means gamma must be greater than 3 alpha, na? The apparent expansion must be positive, greater than 0. So that means gamma is greater than 3 alpha, the liquid will actually overflow. Clear with that? Vice versa. If the temperature decreases, in which case will it overflow? Gamma less than 3 alpha. The reverse. Because now the container will shrink more than this thing. Clear with this? Let's say Mumbai may suddenly temperature drops to minus 30. What do you think will happen to the buildings? I know we go outside and make ice cream, but let's say before that, what do you think will happen to all these glass buildings? If you ever seen a glass ka thing, right? We have a metal frame, and in the middle you have a glass. the temperature suddenly drops, the metal will compress more, the metal will contract more compared to the glass. So basically, the glasses will literally get crushed. So you will glasses, all the glasses will crack. They literally shatter. Next time when you go to a mall, and when you see these big things, observe how they place the glasses. They have glass panels like this. They have some kind of a machine kind of thing with legs like this. They are holding the glasses together. And if you observe, right, there is a gap between them. Like, they keep a small gap between them. Because in India, right, summers get very hot. You need some space for the glasses to expand. If they keep it exactly without a gap during summers, it'll expand so much, the glasses will shatter. Something similar also happens with, railway tracks. We call this thing buckling. Where is this guy? There. Can you see what happened to the railway track? So when the temperature rises, right, and gets heated up, the tracks will start pushing each other, right, and the buckle up. This is called buckling. The entire track will just bend. This is pretty bad. They would prefer if the track actually breaks. That is more easy to repair. This thing is messed up. So if you see the old railway tracks now, that's why normally also they keep a slight space between them. Why all that? Ever gone on a flyover? When you're going on a flyover, next time observe, your vehicle is like tuck, 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 tuck. It keeps hitting. There's a continuous sound. And when you actually look down, you'll observe your flyover is not continuous. The flyover has a thin gaps between them. Section to section ke beech mein there is thin gaps. So when your car or vehicle goes over that, you get that, tuck, 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 tuck kind of thing. Why all that? If you see the train ka sound also, ever heard train ka sound? Can you imagine train ka sound? Tak, 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 meaning I'm not able to say that, but you can imagine, right? That sound. So that sound which you get is because of the same thing. The railway track gaps, right? Whenever the wheel goes over it, you get that sound. So anyway, this is something called buckling. So this is something about liquids. Now, actually, there are a few more questions, but they will come in fluid mechanics. So we will be handling them later on. So there are questions based on elasticity and fluid mechanics in this thermal expansion. We will see them in respect to chapters. So there are a few more models which we couldn't do right now. Next thing is heat. So great. We keep on saying heat and temperature. So what is exactly heat? It's an energy in transit. Which flows from high temperature to low temperature. Or you can say which flows due to temperature difference. Okay. Great. Simple definition. Now let's say I have two bodies here. A and B both are identical. Let's say A ka temperature is 200 degrees. B ka temperature is 100 degrees. Who has more heat? If the bodies are identical except for the temperature, who has more heat? Now the problem with that word is Look at the definition here. It is an energy in transit, meaning, so here the question is, who has more heat? This actually becomes a meaningless statement. Because heat is defined as the energy in transit. Only when the heat is flowing from A to B, there, this is called as heat. Getting it? So when energy flows from A to B, we call it as heat. Once it reaches B, we call it internal energy. We don't call it heat anymore. So only when it is flowing, it's like this, right? What is the difference between a river and a lake? Both have water, right? But river is something like a water body which flows. Lake is something which is stationary. It's end of the day, same thing you're talking about. One is moving, one is not moving, right? It is called heat. So once it reaches B, we call it internal energy. So you can say like this, A has more internal energy than B. That makes more sense. Clear with this? Now, if I ask you something like this, right? Ever heard these words lava and magma? You know, magma cannot exist on Earth's surface. Why? Magma cannot exist on the Earth's surface. You know why? Well, the molten material is below the Earth's surface. We call it magma. Once it comes to the surface, we call it lava. You get in the thing there. You just change the terminology there. So magma and lava are one and the same thing. When it is below the ground, you call it magma. Once it is above the ground, it is called lava. So we say magma cannot exist on Earth's surface because you don't call it anymore. You change the name. Clever that. So heat is something like that. Technically speaking, heat is also an energy which is flowing. Then what is temperature then? So temperature is simply it's a property which decides the direction of heat flow. Look at the definition. What is the heat? It flows due to temperature difference. What is temperature? It tells you how the heat flows. These are called circular definitions. It's like where is your house? Beside my neighbor. Where is your neighbor stay? Beside my house. Both the statements are right, isn't it? It's like that. And this is not the first time. Huh? Do you guys remember the definition of a vector? Vector has a quantity, a vector quantity has both magnitude, direction, and obeys vector laws of addition. So to define what is a vector, you need to know first of all what is a vector laws of addition. Can you see that definition? These are called circular definitions. So in science, right, normally whenever you're explaining stuff, this is what will happen. You always explain one English word with more English words. So when you actually go back to fundamentally something, this is always the problem. That's why visualization, picturization, right, is you can understand better, but then you can put things into words. But there is another way to define what's a temperature. We can also say temperature is a function of random translational kinetic energy of molecules. Let's talk about this a bit. So the main important word is this random translational kinetic energy. So first, let's see what is mean by random. This discussion is important. Again, we'll encounter the same discussion about this random stuff in current electricity. All clear with this page? Now, if you consider molecules in a gas or a liquid, and if you try to study their motion, this is what you will notice. Completely random. So the meaning of random is you can't tell what is happening next. Getting it? So there's a technical name for this. It's called Brownian motion. For this, Einstein got a Nobel Prize. So that year he has published 3 papers: Brownian motion, photoelectric effect, and the theory of relativity. 3 papers, groundbreaking papers. Like each one deserved its own Nobel Prize. But then photoelectric effect was controversial because people thought it was a wave, and Einstein said it is a particle. So there was a fight. Relativity they didn't understand for 50 years. So unfortunately, got only one Nobel Prize. So this Brownian motion, right? Now, this thing happens due to molecular collisions. There are so many molecules inside. After collision, right, they'll just keep on bouncing everywhere. You can notice this if you go to your nearest cow gully, right, or that entire street. You'll observe, look at the people, or look at the auto fellow. Like you don't know how he's going. People are just jumping around, going like any way they want. It's completely random. You can't predict the path. But that same auto fellow on a highway, right, he'll be following a lane. It becomes systematic. So when this motion is random, the average displacement is zero, means eventually, given enough time, it will come back to the initial position. So average displacement is zero, therefore the average velocity is zero. So a random motion will not take you anywhere. You have a high energy, but you're just randomly moving around. And this energy is called as random kinetic energy. So kinetic energy can be classified into 2 types. And this guy is responsible for temperature. Now in cricket, right? I'm not sure whether you heard this commentary. Maybe it's an old timer commentary. It's like, today the crowd is, going wild and the temperatures are rising in the stadium. Ever heard the statement? So when you say the temperatures are rising in the stadium means what? Really the temperature is rising? It means like, the crowd is on fire, crowd is shouting, crowd is like doing all nonsense, whatever it is. Think of like this. If I have 10,000 soldiers marching, and if I have a crowd of 1,000 people burning buses, jumping trains, fighting with everyone, beating everyone. Now you tell me which crowd is more rowdyish and random, you say. The 1,000 crowd is more random, right? So don't we say, Ariyar, kya energetic hai? Just imagine if we take 1,000 people doing a candle march. Peacefully, they're just walking with the candles. No one gives a damn about them, isn't it? The same thing, 100 people start closing the shops, burning the trains and buses. Suddenly, everyone wants to listen to what happened to them. Unfortunately, that is how things work. And we say that 100 people ka crowd, right, is on fire. Like, they have high temperature or high energy, even though you have a 10,000 people walking with candles. Getting the difference? So something similar like that. So when you put your hand in a fire or something, what burns you is this. Ever thought about what is fire? What is fire? Must have seen so many times. What is fire? I've been up. Keep saying these things only. Glowing carbon particles and gases. Yeah. What happens, right? See, fire is nothing but highly heated gas. You can simply think of like that. When the gas or air molecules get heated up to high temperature, right? These molecules are emitting a lot of radiations. So what you think, right? That's a scene. Next time when you open your, switch on your stove and switch it on and see, you'll observe. And the gas is coming out. What you're seeing is actually air molecules vibrating and emitting, photons. So fire actually has momentum. Fire is nothing but highly heated up gas. Simply, if you ask me, we can put it in simple words like that. Yeah. So if you have hot air, it doesn't glow, but you can feel it. But as the temperature rises, once it exceeds a certain level, you think that is fire. That's the reason when you switch on your stove, you'll notice initially the first color you see is blue. Higher the temperature, more energetic. More energetic means more energetic photons. Now you tell me between blue and red, which photons have more energy? Blue photons or red? The blue photons, right? So when the temperature is high, you will see the flame is blue. When the temperature is low, you will see the flame becomes reddish. You can see this thing even in the welding machines also, the torch, welding torch. Initially the flame is blue, then it becomes yellowish. Next time when you switch on the stove, observe that. You will see first the flame is blue. As it goes away from the stove, it cools down, the flame becomes yellow. Notice that? So kind of like that. So then what is systematic motion? So basically in a systematic motion, right, you can predict the path. You can tell where the molecule is going to go next. That's simple. If you so basically there are always two parts. In systematic motion, you can predict the path. In random motion, you can't tell what is going to happen next. Systematic kinetic energy. Clear with this? So then in real life, if you see, right, sometimes you'll see a combination of both also. So when I was in 11th, right, my teacher was teaching something like this in chemical bonding, chemistry. Mein. I really couldn't understand it clearly what happened. So every day, right, it used to take us 45 minutes to go home. So my friend Sabir, he used to explain me everything in the bus. So that is our common thing. This guy used to explain me in the bus while going. Smart guy. So learned a lot of physics from him. So this guy asked Sabir in the evening, like, yeah, Sabir, what is this random motion and systematic? I'm not getting it. And he said, he gave me an example. He said these things. He said, Arun, imagine, this Ganapati procession. You know, Ganapati Visarjan. Now, if you look at that procession going off, if you look at the people around the procession, people are just jumping, dancing, they're doing anything. And if you look at this person, right, you can't tell what he's going to do next, isn't it? Someone might come and push him. This might be jumping, dancing. They're doing everything. But if you actually look at the procession is going aram say and slowly. You know the path. You know this is how the procession is going to go. As the procession goes from here to here, the randomness also goes with the procession, isn't it? You have a random motion which is moving in a predictable path. You can't tell exactly how each person is moving, but you know the overall randomness. The person is always going to be within the procession, isn't it? And if you look at the speed of the person is actually moving pretty fast, but the procession is only maybe going 1 kilometer every 1 hour. You're getting the difference? So the actual motion of this person, right, is actually the speed of the procession only. If the procession goes here, he will travel this much net displacement. But if the procession doesn't move, he's just there dancing around everywhere. I think that's a very decent example. So people around the procession are going in random motion, but the procession itself is going at the systematic velocity. Making sense? Something similar exactly happens in current electricity also in wires. The electrons are moving randomly, but the electrons are being dragged by the battery electric field. So you get a systematic motion plus a random motion. The gas molecules, right? These things have a speed of around 2 to 3 kilometers per second. So currently you're sitting there, the oxygen molecules are hitting you with a speed of 2 to 3 kilometers per second. That's what you think as air pressure. Clear? Now, let's see a question on this. So let's say we have a truck. Let's say we have a container. Let there be some liquid at 80 degrees. So initially the truck is at rest. Container with the liquid is placed in the vehicle. Now, the question is, if the vehicle starts moving, what happens to the kinetic energy of the liquid and what happens to the temperature of the liquid? What happens to the kinetic energy of the liquid and temperature of the liquid? Increase, decrease, remain same. So vice versa, what is cooling then? What do you mean by cooling then? So when you have a refrigerator, what it does, it is basically taking away all the energy from the molecules. The molecules are moving much slower. So when you touch something, you feel it is hot or cold. What are you actually experiencing? Listen, let's say if you look at your finger, the molecules in your finger are also vibrating. They're continuously vibrating. So when you go and touch a hot object, now in the hot object, the molecules are vibrating with bigger amplitudes. Now approximately molecular size is same. So now you tell me, if your hand molecules are going like this, let's say with velocity v, and the molecule of that body is going with 3v because it is hotter. If two bodies of same mass collide elastically, what will happen? They exchange velocities. So after collision, this guy will gain a speed of 3v, this guy will gain a speed of v, meaning the metal will actually cool down and your finger will gain more energy. That is what you think is heat. That's the reason you find something is warm. Similarly, when you go and touch an ice block, your molecules are vibrating more faster than the molecules of the ice. Your temperature will drop, so your molecules lose energy and these molecules gain energy. So when you touch something, the feeling that you get, right, this is hot, this is cold, is nothing but the transfer of energy due to molecular vibrations. We call this thing conduction. So what about this thing? So if I start moving the container, what will happen to the kinetic energy of the liquid and what will happen to the temperature of the liquid? What do you think will happen to the kinetic energy of the liquid? Definitely it will increase. Now, if you see, kinetic energy of the liquid has two components. It has a random kinetic energy. The molecules are just moving randomly. And you have a systematic kinetic energy. So now you tell me, is the vehicle going systematically or randomly? Systematically, right? So this component is increasing. The molecules started going more systematically. So if you take a glass of water and start running, temperature won't rise. There is a random kinetic energy didn't increase at all. So this is actually constant. Therefore, temperature is constant. That is the reason of writing the statement. See, it depends on random kinetic energy. It's not kinetic energy. You can increase the kinetic energy of the system without increasing the temperature. Clear with this? That means if you put two kids in a room and they're doing all nonsense, tearing toys, breaking and everything, and put them in a bus which is going with constant speed and they still do the same nonsense, right? The randomness is still the same. Is that making sense? Kind of like that. And if you and niece are there, they do all that nonsense. My mom says that only. It is better to have four pigs in the house. They're more neat. Kids are like that, can't help it. So now if you actually look at the motion there, now when the container was at rest, if you look at the molecules, they are going like this. This was completely random. But when the container moves, this is what you'll observe. This is the path of the molecules. When the vehicle is moving, this is what you will notice. That is a random thing. The green one is the systematic motion. So the systematic motion, the green ones will always keep pushing you in the same direction. Whereas this red thing, red is a random stuff that is just dragging you everywhere. This is how it would be. So this is random plus systematic. This is how the molecules will go when the vehicle is going with the speed. End of the day, the randoms is only the red part. So this is the path of the path of the molecules when vehicle moves. So when you put water in a flask and if you just take it, temperature won't increase. But if you take the flask and shake it, due to the collision with the walls, the motion becomes random and the temperature rises. Is this clear, everyone? Clear? Next one. Great. So there we have a little idea about temperature and heat now. This is just a discussion, nothing there. But yeah, this was actually a question in one of the exam. If you take a glass of water and start running, what happens to the temperature? Because somewhere people started thinking temperature depends on kinetic energy of molecules. That is wrong. It doesn't depend on kinetic energy of the molecules. It depends only on the random component. Clear with that? Next thing. So there we got something about temperature. So then how do we measure this? So we use thermometers. So if you look at thermometers, they're designed to measure the change in property. For material which is proportional to the change in temperature. I'll tell you what it means. You won't measure the temperature directly. You need to find some kind of property which will change with temperature. So what you actually see is that, and you relate that to the temperature. It's like this. What does a spring balance actually measure? What does a spring balance actually measure? It measures tension in the spring. But what it shows you is tension by G, isn't it? That is what we take as mass. So a spring balance doesn't show you mass. It doesn't know what the mass is. It knows what is tension. So we are going to do something similar. So remember this thing, temperature scales are always linear. So first example, this is what we use now, generally most of the time, the resistance-based thermometers. So when you get a fever and you take a thermometer and put it in the mouth, these things work based on resistance. The idea is this, inside you have a circuit which has a resistance, let's call it R naught. We have an ammeter and we have a small power supply. Now the current I in the circuit will be V is V by R naught. Now this resistance of this thermometer, it's very sensitive. So resistance will be R is equal to R naught into 1 plus alpha delta T. This is the change in temperature. So when you change the temperature, even resistance changes. So when you put a thermometer in your mouth, the temperature, let's say if you have fever, there'll be more temperature. They'll get more resistance. So the new current in the circuit will be, so I new will be V by R naught into 1 plus alpha delta T. From here, they find the change in current. So change in current will be I minus I new which is V by R naught. This would be 1 minus 1 by 1 plus alpha delta T. I can use binomial approximation, so we'll get V by R naught into alpha delta T. There you can clearly see the change in current is proportional to change in temperature. So the thermometer, what happens is that the current inside changes, and the change in current is plotted with respect to temperature. So whenever the temperature changes, so let's say the current changes by 0.01 ampere, we can say the temperature changed by maybe 1 degree or 10 degrees. Temperature changes, resistance changes, this will give you the current changes. So this is how you construct it. You have to make it very sensitive. Even for a small temperature change of 2 to 3 degrees, you should get a decent amount of current. So the system doesn't know what is temperature. Have a look at this. Clear with this? So this is one type. The old standard one, if you see, right, when you're a kid, you must have seen that mercury-based thermometer. So in a mercury-based thermometer, right, you have a bulb here. Inside it is filled with mercury. So when you increase the temperature, the liquid expands. And when the liquid expands, it will push through that stem. So this is called bulb and that is called stem. So this change in height is proportional to temperature again. So here this H will be proportional to delta T. So this length of the mercury column. So what you actually see is the mercurical length, and that's how you relate that to temperature. We also have something called radiation-based thermometers. These things work based on the wavelength of the photons. These are useful to measure, very high temperatures like 1000 degrees plus. Think about it. In a steel factory, when you want to measure the temperature, you can't use any regular stuff, they will melt. So these things, right, are based on wavelength. Low temperatures, they don't work well because there's a lot of other photons, things get messed up. High temperatures, it works really well. This is based on the wavelength of photons emitted. It works at high temperature. Then we also have something called gas-based thermometers, but idea is same. It kind of a liquid only. Yeah, there are a few examples. So the main idea is that somehow you get a property which changes linearly with temperature and use that to make a thermometer. Clear with this? We call this thing calibration. Did I tell you about this thing? We did a project, in IIT, we made something called an anemometer. Did I tell you how we made it? So the thing, right, when we are in first year in IIT, first semester, we had a project from the design team. They gave us 3 projects. I don't remember the other 2, but one of them was an anemometer. Anemometer is simply an instrument which measures wind speed. Okay? And the condition was like this, and you have to form a team of 3 people. All 3 must be from different branches. And you get 1 week time. You can choose 3 projects. I don't remember what is the other 2, but like I said, anemometer we took. So we have to construct one. So idea was simple. The moment they said anemometer, have you ever seen an anemometer anywhere? You can see this thing near metro or weather station or something. The idea was it looks like this. You have a cup here, you have a cup here, you have a cup here, and you have a cup here. So whenever the wind comes, this thing starts rotating. And based on that rotation, you can tell what is the wind speed. If you have ever seen that, next time observe keenly, you will see this thing. I found this in Ghatkopar metro also. Weather station, so it will be there. So this was the idea. We said, "ठीक है, the idea is great." So they gave us access to workshops and everything. We can go to the electrical lab, the mechanical workshop, building. Sab de diya. Matlab they said, do whatever you want. This 1 week you have access. This is 20 years back. Huh? Now, to you have much more better, this thing options. So then we came up with a design. I said, yeah, we will make that cup ka thing. We are too lazy to come up with anything new. So we brought some plastic balls. We cut them in half because plastic balls are lightweight, empty plastic balls. So then somehow, yeah, but it was a headache, huh? Meaning idea was simple, but how do you connect a plastic ball to a metal rod or a wooden stick or something? So we had to come up with different ways of figuring it out. Finally, we made that, the cups kind of thing. The design was simple. And score bhi aisa hai, huh? The exam is for 50 marks. So 50 marks practicals, you have to make that. 50 marks is for theory. In 50 marks, you get 10 marks for unique design. So if you use a standard design, you'll get only 5 marks. If you make something unique, you'll get 10 out of 10 marks. Uh, I think 15 marks if it works properly, and 10 marks it was for the cost. If you very use expensive stuff, then marks will be less. The cheaper the stuff, it is 10. Then kuch to tha, I don't remember what it was. So there were like 4 or 5 criteria, right? And we came up with the design grid. So we made this thing. We somehow attached this balls here, that half hemispherical stuff. Now the problem we faced was this: how do I know if this is rotating, we'll get something? So this was, I said, let's do one thing. We connected this to a dynamo. If you ever seen a dynamo, so when this thing start rotating, you'll get a voltage across the dynamo. So great, I said great. So when this thing rotates, we get voltage. If it rotates faster, we'll get more voltage. So the problem is we didn't know what speed is what voltage, right? Idea to sahi tha. If it rotates faster, we'll get more voltage. But which speed is giving how much voltage? So that we got stuck. 3 days sub design kar liya. Now we are not able to figure out what is the voltage. And first of all, chalo, I will rotate this also. I'll get an ammeter and measure the voltage. How do I know what is the speed, right? Then we started asking people and we noticed everyone had the same problem. Then Abhi, the thing is this: we want something to tell us what is the wind speed. From there we can measure the voltage. We went to aeronautical department. So in the aeronautical department, right, they have a wind tunnel. It can generate wind speeds from 0 to 120 kilometers per hour. So we went to them and we asked them, boss, we want to use the wind tunnel. We want to calibrate our machine. They said, okay. So they opened it on Saturday afternoon. They said Saturday afternoon, it will be open from 1 to 5 p.m. So you can come, you can bring your equipment and check it out. So we went around 2 o'clock or something. So this is what they're doing. They're sending five people inside. So the professor is not there. Some student is there, senior PhD guy. That guy said, I will keep 4 different speeds. Huh? One speed was 10, 20, 30, 40. I'll keep each speed for around 20 seconds. So you can measure whatever readings you got. So we'll get 4 voltages. For 4 speeds, we'll get 4 voltages. From there, we can plot it. So we went inside. There is a table there. We kept our thing on a table. Wind speed was 10. We measured the voltage. Wind speed 20. Our thing became an helicopter and started flying. So every nonsense will happen when you actually make stuff. On paper and everything looks good. Some person that fell down and broke. They had to make a new one. Every nonsense was there. We got 4 readings, and then we thought it will be a linear scale. So we said like wind speed versus voltage, something like this. The values are pretty weird. One was like this, this. Aisa kuch aaya tha, 4 values. And if you join, then you'll get like this. What to do with this? As usual, what to do? We manipulated the data. We pushed it here. We made it align. We did some nonsense with the data. We manipulated it and said, okay, this is the wind versus voltage curve. Some nonsense we did. Then we went to this thing to final that day of submission. We went there. Our teacher brought a table fan. Remember, regular table fan में 3 switches होते हैं ना, 3 speed, low speed, medium speed, high speed. Now this guy comes and says, "I'll switch it on." Right? It should not touch the equipment. It shouldn't become an helicopter. right? And then it should tell what is the wind speed of the fan. Yeah, it was nonsense. Yeah, matlab, it was falling down. Any nonsense was happening, but I think they felt mercy on us. We got around 34 marks out of 50. I said, "Okay, we are happy for it." The highest was 47. That guy made a very unique design. Matlab, he made a windmill kind of design. Then what he did, he kept all the wind speeds here 0, 5, 4, 3, 2, 10, and he kept a rubber band here. When this thing rotates, the rubber band will compress and the needle goes up and down. वो बहुत interesting design था. I don't know how accurate it is, but professor really liked the way it was done using a rubber band. He said this is we got around 2, 3 marks or 4 marks for design. He said this is hopeless design. Like everyone was bringing the same thing. They said there's nothing unique about it. So TKR, that unique thing only was not working. We have struggled for almost 3, 4 days. So yeah, it was fun. So we call that thing calibration. So when you make an equipment, right, how do you know what temperature is what? So you need to have something to check it out and then design your equipment. Great. So then comes up, okay, so we made a thermometer. Now then how do you actually measure them? So we have temperature scales. The most common ones we use is Celsius scale. Celsius scale is more intuitive. People said the most common available substance is water on the earth. So the thing, when you design something, right, you should make sure it is, you should be able to replicate it easily. Means if you design something in India, the person from Australia, right, should be able to make the same thing in Australia also. It can't be like it'll happen only in India. You can't do such kind of nonsense, right? So how do we define that? We define 100 degrees Celsius as boiling point of water at 1 atm. That is important. Atmospheric pressure. So if we can make one atmosphere pressure, water will boil at 100 degrees in Australia or US, even in Antarctica also, as long as you maintain one atmosphere pressure. Now, if you increase the pressure, actually boiling point increases. If you decrease the pressure, boiling point decreases. So if you climb a high hill, like, this Himalayas and all, 3,000, 4,000 meters ka top, the water boils at 70, 80 degrees only. Your pressure cooker, inside the pressure cooker, water boils at 150 degrees. That is the reason your rice cooks faster. Normal water boils at 100 degrees, so the rice is taking heat from 100. But when the water boils at 150 without becoming steam, the rice is getting heat from 150 degrees, so it cooks faster. And how do you make that? All this thing, right, works because of that whistle on the top. By putting that whistle weight on the top, right, in order to push it out, the pressure increases inside to become 2 to 3 atm. The pressure is almost 3 times atmosphere pressure. The water boils at 150 degrees. The rice cooks faster. So when I was a kid matlab, third or fourth standard, I guess. So I wanted to help my mom. So there was a rice cooker there, and this thing whistle is blowing and steam is coming out. I said, "Yeah, shit, Ray, steam is leaking." Getting it means all the steam is getting wasted. I need to help. Karke, I took a glass of water and kept on top of it. I added more weight. The what happened? The whistle was not blowing because weight ज़्यादा डाल दिया था. So inside the pressure went on, went on, went on, and the cooker, if you ever observe, right, there is something called a safety valve. Ever seen that? Cooker ka side में there's a safety valve. That thing blows off when the pressure exceeds 5 atm. That blows off. It's a safety valve. If that safety valve doesn't work, you have created a bomb. The pressure cooker will literally blast, right, and things will be bad. Safety valve blowed off. The pressure cooker ka handle melted, right? So these are the things. Evil things happen not because you're evil. You had good intentions, but you're dumb. The pressure cooker, literally, the safety valve blasted. Mom came and blasted me right and left. It was a nonsense. The rice just spilled everywhere, meaning it was gone completely. Cooker was gone. We had to buy a new one. The steam has a very high pressure. So that is the first time with the kitchen. That is not the only time. I messed up multiple times. Same thing. I wanted to help my mom. I said, I'll help you. She said, okay, go wash the rice. I took the rice, went to the bathroom. She waited for me 5 minutes. She didn't see me. I went into the washroom. She came and said, what the hell are you doing? I said, I'm washing the rice. I kept first surf. Then I washed it properly. Then I cleaned it. Then I said, these things will have germs also. Then I added Dettol. Then I cleaned it second time. Said the mom didn't understand whether to laugh or cry. We had to throw that rice. She said, "You don't wash rice like that." I said, "Yeah, when you go and take bath, don't you use soap? And now you're going to wash rice, which you're going to eat. Shouldn't you wash it with the Dettol and all?" I think that was the last time I entered into the kitchen. After that, she never gave me anything to help in the kitchen. Anyways, so this is the melting point of ice. It's not because, the thing, no, the difference is that 10, 15 years back, right, we had nothing to do, right? People, if you see kids right now, they don't do all this kind of nonsense. People are too smart. Right? They're too busy with their phones, Instagram, YouTube shorts, and all. So we had to figure out everything on our own, right? So we used to be dumb and we used to do nonsense things. Meaning, I'll tell you, when I was a kid also, I used to see movies, right? In a movie, end में the hero dies. Then the same guy comes in second movie. You know what I used to think? Twins. First twin died, second twin came. I used to see him again in third movie, triplets. So from this, I made a conclusion. If you want to be a villain in a movie, you should be either twins or triplets. Only these people are allowed to be villains. That was my whole concept there. I think out of all these nonsense things, the highlight was this. One day I saw an ad in the TV. Okay, it's a Melody chocolate ad. I don't know whether you know what's a Melody chocolate. Right? कुछ तो था. In the chocolate, there's an ad. The brother and sister both go to the chocolate ka shop. They get a chocolate. They eat the chocolate and they rotate. They get new dresses. That was the ad. I got a super idea. I said, I'm going to surprise my mom. I went to the shop. I brought two chocolates. Came to the room, closed the door. I ate the chocolate. I started rotating. After rotating 4 or 5 times, nothing happened. I said, chocolate is defective. Happens. Equipment can be defective. Then I ate the second chocolate. I started rotating almost for 10 minutes. Nothing happened. And then I understood, bloody, I got fooled. It doesn't work. So there, that is how dumb we used to be. At least I was really dumb. I was curious. I used to take things on face value. The next one is a Fahrenheit scale. I think I was in third or fourth standard, I guess. Fahrenheit scale is 212 degree Fahrenheit and 32 degree Fahrenheit. This is one of the most useless scale. Not sure who created this or why they created this. That numbers don't make sense. There is no logic. Could be something logic, but I don't know. Celsius 0 to 100 इतना अच्छे से दिख रहा है symmetry. 32 and 212, I don't know who cares. And we know the conversion factor Celsius scale is given by 5 by 9 F minus 32. Should know this. Now, out of the three scales, if you ask me, the more prominent one is a Kelvin scale. This is more scientific. This is also called as a universal scale. Meaning, tomorrow if aliens come to the Earth, we can be sure they also know something about Kelvin scale. Why is this so special? So Kelvin scale 373 Kelvin and 273 Kelvin. The relation is Kelvin scale is Celsius plus 273.15. The reason for this thing is when you take any gas, any pressure, you take oxygen, you take helium, you take nitrogen at any pressure. And if you plot volume versus temperature graph, people notice this. You plot any VT graph, and when you extend them, they observed independent of the type of the gas. All these gases, they always meet at minus 273.15. Means at this temperature, the volume becomes zero. And it is really profound. Matlab, socho, if there's an alien on Pluto where the temperature is minus 220, if that guy has access to methane gas and does this experiment, even he will observe at this particular point the volume tends to zero. So this Kelvin scale is a universal scale where if alien civilization is really smart enough, right, they will understand this is the scale they have to use. So when they come to Earth, right? You switch on the fire and show them the thermometer. That alien will understand you're talking about temperature. He will bring out his own equipment. So you can be sure like that guy is talking about Kelvin scale in his own language. You're getting it? So this is more fundamental. He won't understand what is Celsius scale. Fahrenheit scale, so we only don't understand, right? So Kelvin scale is like a universal scale. Everyone will understand. Again, scientific scale it is. Because no matter which planet you take, which gas you take, which temp, anything you take, the graph will look like this. Ideal gases tend to zero volume because you can't have anything less than zero volume. It doesn't make sense. At minus 273.15 Celsius. So people said, yeah, this is more fundamental, and that's why we take that minus 273.15 as 0 Kelvin. Clear with this? So out of the three scales, Kelvin scale is the more fundamental one. So all temperatures, everything, right? We measure in that. So let's say, imagine tomorrow aliens come to the Earth, right? And one of the alien ambassadors falls sick. Unfortunately, they don't have any doctors on their spaceship. Right now, if the ambassador dies, the aliens will think you killed them and they'll come for war. Now, in order to save that alien ambassador, which doctor will you send? You have access to all the doctors on the earth. You can get the best of the doctors. No, whom will you send to save this alien? What do you think? If you send any world's best human doctor, they're going to kill him. Human doctors have a problem. They are trained so well to work with human bodies, they don't know how an alien body works. You send the world's best veterinarian, vet doctor, because the alien might have three hearts. A human doctor will go mad. He'll not understand what the hell happened. But if you see a vet doctor, right, he must have treated an octopus which has eight hearts. That guy works with different animals, isn't it? A dog, a cat, a penguin, mongoose, snake, right? So fish. So that guy has more idea about anatomy of different animals than a human doctor. So you get the world's best vet doctor and you treat him. So it doesn't mean alien is an animal, but yeah, that is our best shot. Yeah. So if you think things make sense, okay, take a break, come back with 7, and we'll continue from here. Okay, come back in 10 minutes. Let's see a question. First one is a standard one, which you must have seen in your school. Find the temperature at which Celsius and Fahrenheit scale show the same number. Means that temperature, right? Both should measure the same thing. That's an easy one. Next thing. Now, someone designed a new scale called M scale. Is defined such that melting point of ice is at minus 20 degrees. Sorry, melting point of ice is 20 degree M. So someone, just like F scale, Fahrenheit scale, someone defined something called M scale. Boiling point of water at 70 degree M. Then find the relation between M scale and Celsius scale. Just like you have a relation between Celsius and Fahrenheit scale, I need to find a relation between M scale and C scale. Get them both. Yeah, first was easy, minus 40. That's a standard result. Get the next one. Others do keep your cams on. Means I want you to find me an answer like this. The Celsius scale was what? 5 by 9 F minus 32, like that. You have to tell me M is equal to what in terms of Celsius. Right, Puraja. Right, Aryaman. Others, give it a try. I'll give you 1 more minute. Let's see. First was easy. Celsius scale is 5 by 9 F minus 32. You're saying C is equal to F. So this will be 9C, this will be 5C minus 32. You solve this, you end up with minus 40. That minus 40 degrees Celsius and Fahrenheit, both are actually talking about the same temperature. This thing, now we know temperature scales are linear. That means you can write M is equal to some constant A into Celsius scale plus B. Basically, you can write in the form of y is equal to mx plus c. So when Celsius is 0, m is 20. So this is a into 0 plus b. So that I got b ka value is 20. When Celsius is 100, m scale is showing 70. So that will be a into 100 plus b is 20. So a is half. There. So substitute here. So m is equal to c by 2 plus 20. Easy. Or you can find the other way around. C is equal to 2m minus 20, 2m minus 40, both the same. So exam, they'll give you something like that. If the Celsius scale is showing 55 degrees, then what will M scale show? You can substitute there and figure out the temperatures. Clear with this? So there, that is a little about heat and temperature scales and thermometers and stuff. Little bit theoretical, but next thing, calorimetry. So calorimetry, it deals with relation between heat and temperature. So first thing, we define something called a calorie. So calorie is the amount of heat required. To increase the temperature of water from 14.5 degrees Celsius to 15.5 degrees Celsius at 1 atm. So normally this is how we take it. So that means if the water is going from 90 to 91 and 20 to 21, it is not the same amount of heat. There's a slight difference, negligible difference is there. So for our convenience, right, we assume it is same. So we don't take like this 99 to 100, 0 to 1, 9 to 10, we will assume everything is same. There is a slight difference though. We assume it is same for any 1 degree change. Now after this, another thing which you'll keep hearing right in your book and in the class in this questions and stuff, there is something called mechanical joule equivalent. The word looks very scary and all, but it means nothing. The story goes like this. Initially, when people are working on heat, people thought whenever you want to increase the temperature, the only way you can do that is by giving heat. That means you put a fire or something and only then you can increase the temperature. But take your both the hands and rub them. Don't the hands become warm? Are you putting any fire? So basically, you are giving work and your temperature is rising, isn't it? If you put your both the hands and rub them against each other, your hands do become warm without giving any heat or fire or anything. So, but people initially, right, they used to think, yeah, temperature alag hai, heat is different, energy is different. But later on, when they realized, so the people who studied heat studied everything in calories. People who studied work, they studied everything in joules. They thought these two are completely different. And then later on, when they realized, boss, heat is nothing but another form of energy, then they said, okay, and then let's make everything into same. So then we had a conversion factor. So mechanical joule equivalent, the symbol is J there. So what it simply means is it's a conversion factor. That's it. There is no physical significance of this. It's a conversion factor between calories and joules. So 1 calorie is 4.18 joules. We'll round it off to 4.2 joules. So when you hear that word next time, mechanical joule equivalent, understand that it is simply a conversion factor. Clear with this? Next thing. Consider a body of mass M at temperature T. Let dq a small amount of heat. Q is a symbol we use for heat. Let dq heat be given and temperature rise by dt. So if you have a body here at temperature T, so when you give a small amount of heat dq, the temperature becomes d plus dt. So the formula goes like this. So dq, it depends on how much mass is there. It depends on a constant called s, and it depends on dt. So this is the formula. dq is ms dt, where q is equal to integral ms dt in case mass or dt something is changing. Here m is the mass of the body. S is called specific heat capacity. So S is nothing but 1 by m dq by dt. The amount of heat required to change the temperature per unit degree per unit temperature. Per unit degree per unit mass. It depends only on the nature of the material. So different materials have different S. The physical significance is this. Higher the S, more difficult to change the temperature. Think about it. If S ka value is more, means what? Require more heat to change the temperature. Now, this is what we use for solids, liquids, and everything. But for gases, what we do, I'll just write it here. For gases, we prefer to study dq is equal to nc dt. I'll write in the next page. There. So this would be the main formula there. So this gives you the relation between the heat and temperature. How much heat should I give to change the temperature by dt? dq is ms dt. If s is a variable or m is a variable, then you have to integrate. We generally use this for solids and liquids. For gases, mass really doesn't make sense. We use moles. That is the meaning of specific heat capacity. Higher the specific heat capacity, more difficult to change the temperature. Clear? So dq is ms dt. So S is 1 by m dq by dt. For gases, we write dq is nc dt. N is the number of moles. C would be 1 by n dq by dt, the amount of heat required to change the temperature per mole per unit degree. This is called molar heat capacity. So basically that m into S is nothing but n into C. It's the same stuff. Now you need to remember certain values. For example, if you take S of water, and if you remember, that's how we define calorie. It is 1 calorie per gram per Celsius. Means to change the temperature of water by 1 degree, you need to give 1 calorie for 1 gram. Same thing, if you take S of ice, it is half calorie. Means to change the temperature of ice by 1 degree, you need to give only half calorie. Same thing with the steam also. So steam and ice, the specific heat becomes half. Water is 1 calorie. So different materials are different. But these values you should remember for water and ice. For other objects, they'll give you normally. Clear with this? Now here I can ask a theoretical question. For a liquid in a thermometer, if you want to use a liquid in a thermometer, should it have high specific heat capacity or low specific heat capacity? Should it have high volume expansion, coefficient of volume expansion, or low coefficient of volume expansion? Meaning we're talking about S and gamma. I want to create a thermometer with a liquid. Now that liquid should have high specific heat capacity or low specific heat capacity, high coefficient of volume expansion or low coefficient of volume expansion. What do you guys think? Again, ask yourself, what is gamma? Gamma tells you higher the gamma, more easily liquid will expand, isn't it? Higher the specific heat capacity, more difficult to change the temperature. So what should be there? Both high gamma, highest, high specific heat, low gamma, low specific heat. Again, let me ask you this thing. So for this liquid in the thermometer, right, when you put it in the mouth, you want the thing to respond immediately or you want it to take time? You want it to respond immediately. That means even for a small amount of heat, you want the temperature to change or not change. Right? So when you put it in the mouth, even for a small amount of heat, you want the temperature to change, isn't it? So if the temperature has to change easily, then specific heat capacity must be less. Because you want it to change the temperature with even small amounts of heat. You don't want to put in the mouth for 1 hour and then supply heat. It should have less specific heat capacity. Reason? Temperature should change fast. And what about gamma? So when the temperature changes, you want the liquid to expand more or less? Let's say if the liquid expands only 0.1 millimeter, can you see? So you want it to expand substantially, meaning so. For 1 degree temperature, if it expands 1 centimeter, 1 degree it expands 1 millimeter. Which one is more easily to visible to see? So 1 centimeter, right? So it means you want it to expand easily. So gamma should be more. So even for a small change in temperature, liquid expansion should be more. They can ask you theoretical questions like this. So if this happens, thermometer is more sensitive. So for low specific heat and high gamma, thermometer is sensitive. Sensitive meaning you will react even for small changes. That is how you want an equipment to be. You want it to respond to as small temperatures as possible. We say, Arey, this person is very sensitive. You say something, he feels bad. So equipments, you only want them to be sensitive, because if they're sensitive, you can measure even 0.1 degree. Let's say if it is not sensitive, that means until unless temperature changes by 10 degrees, it won't move only. It is useless. You won't be able to measure stuff. Clear? Let's see a question. We have a rod here. Mass M, length L, quotient of volume expansion, linear expansion. Specific heat capacity of the rod. Now what you did, you gave heat Q to the rod. The floor is smooth. Find the change in temperature of the rod. Assume all the heat is absorbed by the rod only, so there is no loss. So we're assuming rod is not cooling down, all that stuff you can ignore. I gave heat Q to the rod, it took everything. What is the change in temperature of the rod? Q by MS. Listen, there is a catch. That formula Q is MS delta T means what? If you want to change the temperature by delta T, I need to give heat Q. But here something is happening. So when I give temperature to this rod, it will expand, agreed? Now when it expands, look at the rod, how it looks. So initially this was the rod. Now the rod has become like this. Mass didn't change. But what happened to the center of mass? Center of mass has gone up a bit, isn't it? That means if you take this height, L by 2, Now the center of mass is at a height of L by 2, 1 plus alpha delta T. Whatever is the bottom expansion, that will push it up. So the change in center of mass will be L by 2 alpha delta T. So my question is, who gave this extra potential energy? It must have come from somewhere, right? So the heat Q given, it goes for gravitational potential energy plus ms delta T. So there are two components. All the heat didn't go for temperature. You used some of the heat in order to raise the center of mass of the body. So this would be mg delta h center of mass. The potential energy is that ms delta T. This would be mgl by 2 alpha delta T plus ms delta T. So delta T will be q by mg l alpha by 2 plus ms. Makes sense. If it's a simple question in mains level, I'll ask you like this. I have a rod like this, I have a rod like this, a horizontal rod and a vertical rod. Exactly, both are identical, everything is same. If I give same heat, who will have more temperature, the horizontal rod or the vertical rod? That would be a proper mains theoretical question. A rod is placed horizontally, rod is placed vertically. If I give same heat, who will have more temperature? The horizontal, right? Because horizontal rod will expand like this, so there's no change in potential energy. Vertical rod will expand like this. You used some of the energy to increase the height. Makes sense. They did ask a question like this in JE Advance. I changed it and I made it into like this. The question in the JE was this. They said there was a solid sphere here, and there's one solid sphere hanging from the ceiling, hinged at the center. Same question they said. When I give heat Q to the thing, which one will have more temperature? So this upper ball, which is hinged in the center, will expand like this. It will expand in all directions, so centromos does not move. Whereas this ball, bottom it is ground is there, so it will push itself. So centromos will go slightly up. So this ball which is in the air will have more temperature than the ball on the ground. Is this making sense, everyone? There. That is how you can frame a question. What? You thought centromos is over? Your mechanics will keep haunting you. Clear with this? Let's see one more like this. It's a good one. We have a spring here. We have a rod here. We have one more spring here. K1, K2, mass M, length L, alpha, specific heat S. Springs are in natural length. Now what you did, you gave heat Q to the system. Find the change in temperature and the compression in the springs. Just get me the equations. Solving will be a little bad. So total there are how many variables? 3 variables. 2 compressions and 1 change in temperature. So I need 3 equations. In this process, right, generally when the rod is getting pushed, it has energy. We'll ignore that. Assume the rod does not store any energy because of this compressions. Assume no elastic energy in the rod. There, give it a try. Get me the equations. What are the other equations? You'll get three equations you need to solve three variables. Right, Vihan. You got them. Others, try. I'll give you a minute. Let's see. So the rod will expand. Let's say initially this length was L. Now this length is L into 1 plus alpha delta T. So let this thing compress by x1, let this thing compress by x2. So can I write x1 plus x2 will be L alpha delta T, the change in length of the rod? Whatever is the change in length of the rod, where did it go? It went into compression of the springs. Make sense? Second thing, the rod is in equilibrium. That means if you see this force K2 x2 must be equal to K1 x1. The forces are in equilibrium, or else the rod will keep on moving. That was your second equation. Third, where did all this energy go? All the energy went into to change the temperature ms delta T plus the spring energy, half K1 x1 square plus half K2 x2 square. You get a quadratic kind of thing. If your numbers are there, it would be easy to solve. So there, from here you can get x1, you can get x2, and you can get delta T. If you got the three equations, your job's done. Have a look at this. Making sense? Whatever is the rod ka change in length that went into the springs. Spring forces must be equal, or else the rod will keep moving. All the energy you gave went into the springs and ms delta T. Clear? Next one. We have something called heat capacity. This is again not a concept as such, but it is more like a lab ka thing, just like radius of gyration. Now tell me one thing, when you go into the lab and you take a metal or something, do you really want to study like this is copper, this is steel and all? We don't care, right? So what people said here, to make your life easy in the lab, we define something called heat capacity. This is simply the amount of heat required to change temperature by 1 unit. So in the formula dq is equal to ms dt, we replace this with h into dt. So heat capacity is nothing but m into s. Specific heat capacity में is s. Heat capacity is m into s. So the advantage of this thing is, example, let's say specific heat of a material is 100 calorie per gram per cc, meaning to change the temperature of 1 gram per degree you need 100. Let's say if you have a 20-gram body, so let's say you go into the lab and you found a small sphere, 20-gram ka mass. So on the sphere it will be printed the heat capacity is m into s, which is 20 into 100. That would be 2000 calories per Celsius. So this, the manufacturer will take care of it. You're getting it? So on top of that body, let's say you have some random shape. I don't care what is the shape. On it, it will be written 2000 calorie per Celsius. Meaning what? If I give 2000 calories, temperature will change by 1 degree. Simple, right? I need not care what is the shape. I need not care what is the mass. I need not care what type of material it is. Hope you're getting it. It's more of a convenience in the lab. right? We don't want people to figure out the mass, specific heat capacity, and then multiply. Keep it simple. You just so on the bodies you simply print heat capacities. We don't print specific heat capacity. So if you see specific heat capacity, S is independent of mass because it is defined per gram. Heat capacity depends on the mass. So same material, if I take 100 gram ka body, then it would have been 10,000 calorie per Celsius. Is that making sense? So heat capacity is more of a convenience in the lab. Specific heat capacity is actual concept. Clear, everyone? Similarly, we also define something called water equivalent. This is also a lab ka thing. Let's say if you're trying to boil water in a container, now the heat supplied must be equal to the heat taken by the container plus water. So people say, yeah, it is again means I should know what kind of material it is. I should know what kind of mass is it is. It's all nonsense. So what people do is this: the amount of water which gives same temperature change as the body for same heat. So if you have a copper vessel, let's say if you are making a vessel to boil water, so on the copper vessel, it will be printed. The water equivalent is 50 grams. The meaning of this is if you take 50 grams of water and if you take this copper vessel or whatever is the vessel, if I give heat Q, if I give heat Q, both the temperatures will be changed by same amount. Both have same temperature difference. Means you can replace the copper vessel with 50 grams of water. So what is the use of this? So when you go to the lab and you're trying to boil water, let's say you pour water inside. It's 100 grams of water inside. And let's say vessel has, so on top of it, it will be printed water equivalent. Water equivalent is, let's say, 80 grams. Means you can replace this whole setup with 180 grams of water and solve the problem. So what is the advantage? So if I give heat Q here and Q here, so here the equation will be like this: Q is equal to mass of the vessel, specific heat of the vessel into delta T plus mass of the water, specific heat of the water into delta T. So unnecessarily get two terms. And that means I need to give you information about mass of the vessel, specific heat of the vessel. But in this case, you can directly write Q is equal to total mass of the water, specific heat of the water, delta T. Done. एक step में हो जाएगा. You can just treat like this water 180 grams, whereas this thing is 100 grams. Are you getting the difference? So water equivalent and specific heat capacities are more of a lab ka thing. They're more convenient to use. As such, they're not concepts. Just like radius of gyration is not a concept. Is this clear, everyone? There. So these are few things there. So next class when we catch up, we'll continue from here. We will see more latent heat of fusion, latent heat of vaporization, and then we'll see what happens if you start mixing different liquids of different temperature, ice mixing with water, all that stuff. I think that should take first half of the class, and then we'll start off with KTG. KTG would look similar to ideal gas equation. PV is equal to nRT. We'll be playing with that mostly. I think by next week we'll finish off KTG also, and then we'll start off with thermodynamics. Okay, with that we'll wrap up for the day. So make sure to go through this. There are 14 questions, not much. I'll try to send you a small sheet on thermal expansion, because in your booklets, right, questions will be based on elasticity and fluid mechanics also will get mixed up. But like I said, there are not too many questions on this, so I'll send you a small sheet. Okay, with that we'll wrap up for the day. So any doubts, anything, you can stay back and ask you, or else you're free to leave. So make sure to write the exam. It's a deadline till tomorrow evening. So I'll see you guys again next Tuesday at 5:30.